Structure of atom. The existence of atoms has been proposed since the time of early Indian and Greek philosophers 400 BC, who were of the view that atoms are the fundamental building blocks of matter. According to them, the continuous subdivisions of matter would ultimately yield atoms which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were mere speculations and there was no way to test them experimentally. These ideas remained dormant for a very long time and were revived again by the scientists in the 19th century. The atomic theory of matter was first proposed on firm scientific basis by John Dalton, a British school teacher, in 1808. His theory, called Dalton's atomic theory, regarded the atom as ultimate particle of matter. In this unit, we start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. These established that atoms can be further divided into subatomic particles, i.e. electrons, protons, and neutrons, a concept very different from that of Dalton. The major problems before the scientists at that time were to account for the stability of atom after the discovery of subatomic particles, to compare the behavior of one element from other in terms of both physical and chemical properties, to explain the formation of different kinds of molecules by the combination of different atoms, and to understand the origin and nature of the characteristics of electromagnetic radiations absorbed or emitted by atoms. Dalton's atomic theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportion very successfully. However, it failed to explain the results of many experiments. For example, it was known that substances like glass or ebonite, when rubbed with silk or fur, generate electricity. Many different kinds of subatomic particles were discovered in the 20th century. However, in this section, we will talk about only two particles, namely electron and proton. Discovery of electron. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occurred at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated certain laws which you will study in class 12. These results suggested the particular nature of electricity. In insights into the structure of atom obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind a basic rule regarding the behavior of charged particles. Like charges repel each other and unlike charges attract each other. In mid-1850s, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. It is depicted in figure 2.1. A cathode ray tube is made of glass containing two thin pieces of metals called electrodes sealed in it. The electrical discharge through the gases could be observed only at very low pressures and at very high voltages. The pressure of different gases could be adjusted by evacuation. When sufficiently high voltage is applied across the electrodes, current starts flowing through a stream of particles moving in the tube from the negative electrode to the positive electrode anode. These were called cathode ray or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the tube behind the anode with phosphorescent material zinc sulfide. When these rays, after passing through anode, strike the zinc sulfide coating, a bright spot on the coating is developed. Same things happen in a television set. The results of these experiments are summarized below. The cathode ray starts from cathode and moves towards the anode. Second, these rays themselves are not visible, but their behavior can be observed with the help of a certain kind of materials, fluorescent or phosphorescent, which glow when hit by them. Television picture tubes are cathode ray tubes, and television pictures result due to fluorescence on the television screen coated with certain fluorescent or phosphorescent materials. Third, in the absence of electrical or magnetic field, these rays travel in straight lines. Figure 2.2. Fourth, in the presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. Fifth, the characteristics of cathode rays, electrons, do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituent of all atoms. Charge to mass ratio of electron. In 1897, British physicist J.J. Thomson measured the ratio of electrical charge E to the mass of electron Me by using cathode ray tube and applying electrical and magnetic field perpendicular to each other as well as to the path of electrons. Thomson argued that amount of deviation of the particles from their path in the presence of electrical or magnetic field depends upon 1. The magnitude of the negative charge on the particle. Greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic field, and thus greater is the deflection. 2. The mass of the particle. Lighter the particle, greater the deflection. Third, the strength of the electrical or magnetic field. The deflection of electrons from its original path increases with the increase in voltage across electrodes, or the strength of the magnetic field. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, electrons strike the cathode ray tube point C. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path followed as in the absence of electric or magnetic. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path followed as in the absence of electric or magnetic field, and they hit the screen at point B. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the value of E by Me equals 1.75 into 10 raised to the power 11 C per kg, where Me is the mass of the electron in kg and E is the magnitude of the charge on the electron in coulomb. Since the electrons are negatively charged, the charge on electron is minus E. Charge on the electron. R.A. Millikan devised a method known as oil drop experiment to determine the charge on electrons. He found that the charge on the electron to be minus 1.6 raised to the power 10 minus 19 coulomb. The present accepted value of the electrical charge is minus 1.6022 into 10 raised to the power minus 19 coulomb. The mass of the electron Me was determined by combining these results with Thomson's value, which give 9 into 10 raised to the power minus 31 kg. Discovery of protons and neutrons. Electrical discharge carried out in the modified cathode ray tube led to the discovery of particles carrying positive charge, also known as canal rays. The characteristics of these positively charged particles are listed below. Unlike cathode rays, positively charged particles depend upon the nature of gas present in the cathode ray tube. These are simply the positively charged gaseous ions. Second, the charge to mass ratio of the particles is found to depend on the gas from which they originate. Some of the positively charged particles carry a multiple of the fundamental of electric charge. The behavior of these particles in the magnetic or electric field is opposite to that observed for electron or cathode rays. The smallest and lightest positive ion was obtained from hydrogen and was called proton. This positively charged particle was characterized in 1919. Later, a need was felt for the presence of electrically neutral particle as one of the constituent of atoms. These particles were discovered by Chadwick by bombarding a thin sheet of beryllium by alpha particles. When electrically neutral particles having a mass slightly greater than that of protons was emitted, he named these particles as neutrons. The important properties of these fundamental particles are given in table 2.1. Atomic models. Observations obtained from the experiments mentioned in the previous sections have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. Different atomic models were proposed to explain the distribution of these charged particles in an atom. Although some of these models were not able to explain the stability of atoms, two of these models, proposed by J.J. Thomson and Ernst Rutherford, are discussed below. Thomson model of atom. J.J. Thomson in 1898 proposed that an atom possesses a spherical shape, radius approximately 10 raised to the power minus 10 meter, in which the positive charge is uniformly distributed. The electrons are embedded into it in such a manner as to give the most stable electrostatic arrangement. Many different names are given to this model, for example, plum pudding, raisin pudding, or watermelon. This model can be visualized as a pudding or watermelon of positive charge with plums or seeds embedded into it. An important feature of this model is that the mass of the atom is assumed to be uniformly distributed over the atom. Although this model was able to explain the overall neutrality of the atom but was not consistent with the results of later experiments. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. Rutherford's nuclear model of atom. Rutherford and his students Hans Geiger and Ernst Marsden bombarded very thin gold foil with alpha particles. Rutherford's famous alpha particle scattering experiment is represented in figure 2.15. A stream of high-energy alpha particles from a radioactive source was directed at a thin foil of gold metal. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck that screen, a tiny flash of light was produced at that point. The results of the scattering experiment were quite unexpected. According to Thomson's model of atom, the mass of each gold atom in the foil should have been spread evenly. Alpha particles had enough energy to pass directly through such a uniform distribution of mass. It was expected that the particles would slow down and change direction only by small angles as they passed through the foil. It was observed that 1. Most of the alpha particles passed through the gold foil undeflected. 2. A small fraction of the alpha particles was deflected by small angles. 3. A very few alpha particles, almost 1 into 20,000, bounced back, that is, were deflected nearly 180 degrees. On the basis of the observations, Rutherford drew the following conclusions regarding the structure of atom. 1. Most of the space in atom is empty, as most of the alpha particles pass through the foil undeflected. 2. A few positively charged alpha particles were deflected. The deflection must be due to enormous repulsive force, showing that the positive charge of the atom is not spread throughout the atom as Thomson had presumed. The positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. Calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 raised to the power minus 10 meter, while the nucleus is about 10 raised to the power minus 15 meter. One can appreciate this difference in size by realizing that if a cricket ball represents a nucleus, then the radius of atom would be about 5 kilometers. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom after discovery of protons. According to this model, 1. The positive charge in most of the mass of the atom was densely concentrated in an extremely small region. This very small region of the atom was called nucleus by Rutherford. The nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of sun and the electrons that of revolving planets. Electrons and the nucleus are held together by electrostatic forces of attraction. Atomic number and mass number. The presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of protons present in the nucleus is equal to the atomic number Z. For example, the number of protons in hydrogen nucleus is 1, in sodium atom 11. Therefore, their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons, atomic number Z. For example, number of electrons in hydrogen atom and sodium atom is 1 and 11 respectively. Z equals to number of protons in the nucleus of an atom equals to number of electrons in a neutral atom. While the positive charge of the nucleus is due to protons, the mass of the nucleus due to protons and neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of the nucleons is termed as mass number of the atom. Mass number equals to number of protons plus number of neutrons. Isobars and isotopes. The composition of any atom can be represented by using the normal element symbol X, with superscript on the left-hand side of the atomic number A and subscript Z on the left-hand side of the atomic number. Isobars are the atoms with same mass number but different atomic number, for example C14 and N14. On the other hand, atoms with identical atomic number but different atomic mass are called isotopes. In other words, it is evident that difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. For example, considering of hydrogen atom again, 99.985% of hydrogen atoms contain this isotope is called protium. Rest of the percentage of hydrogen atom contains two other isotopes. The one containing one proton and one neutron is called deuterium, and the other one possessing one proton and two neutrons is called tritium. The latter isotope is found in trace amounts on Earth. Other examples of commonly occurring isotopes are carbon atoms containing 6, 7, 8 neutrons besides 6 protons, chlorine atoms containing 18, 20 neutrons besides 17 protons. Lastly, an important point to mention regarding isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all the isotopes of a given element show same chemical behavior. Drawbacks of Rutherford model. Rutherford nuclear model of an atom is like a small-scale solar system, with the nucleus playing the role of massive sun and the electrons being similar to the lighter particles. Further, the Coulomb force kq1 q2 upon r square, where q1 and q2 are the charges, r is the distance of separation of the charges, and k is the proportionality constant between electron nucleus is mathematically similar to gravitational force g m1 m2 upon r square, where m1 and m2 are the masses, r is the distance of separation of the masses, and g is the gravitational constant. When classical mechanics is applied to the solar system, it shows that planets describe well-defined orbits around the sun. The theory can also calculate precisely the planetary orbits, and these are in agreement with the experimental measurements. The similarity between the solar system and the nuclear model suggests that electrons should move around the nucleus in well-defined orbits. However, when a body is moving in an orbit, it undergoes acceleration. Even if the body is moving with a constant speed in an orbit, it must accelerate because of changing direction. So an electron in the nuclear model describing planet-like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiations. This feature does not exist for planets since they are uncharged. Therefore, an electron in an orbit will emit radiation. The energy carried by radiation comes from the electronic motion. The orbit will thus continue to shrink. Calculations show that it should take an electron only 10⁻⁻8 seconds to spiral into the nucleus. But this does not happen. Thus, the Rutherford model cannot explain the stability of an atom. If the motion of an electron is described on the basis of the classical mechanics and electromagnetic theory, you may ask that since the motion of electrons in orbits is leading to the instability of atoms, then why not consider electrons as stationary around the nucleus? If the electrons were stationary, electrostatic attraction between the dense nucleus and the electrons would pull the electrons towards the nucleus to form a miniature version of Thomson's model of atom. Another serious drawback of Rutherford model is that it says nothing about the electronic structure of atom, i.e., how the electrons are distributed around the nucleus and what are the energies of these electrons. Developments leading to the Bohr's model of atom. Historically, results observed from the studies of interactions of radiations with matter have proved immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr's model of atom. These were 1. Dual character of these electromagnetic radiation, which means that radiations possess both wave-like and particle-like properties, and 2. Experimental results regarding atomic spectra, which can be explained only by assuming quantized electronic energy levels in atoms. Wave nature of electromagnetic radiation. James Maxwell, 1870, was the first to give a comprehensive explanation about the interaction between the charged bodies and the behavior of electrical and magnetic fields on macroscopic level. He suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiation. Light is the form of radiation known from early days, and speculation about its nature dates back to remote ancient times. In earlier days, Newton light was supposed to be made of particles, corpuscles. It was the only in the 19th century when wave nature of light was established. Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. Although electromagnetic wave motion is complex in nature, we will consider here only a few simple properties. 1. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. Simplified picture of electromagnetic wave is shown in 2.6. 2. Unlike sound waves or water waves, electromagnetic waves do not require medium and can move in vacuum. It is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength or frequency. These constitute what is called an electromagnetic spectrum. Different regions of the spectrum are identified by different names. Some examples are radio frequency regions, example 10 raised to the power 6 Hz used for broadcasting, microwave region around 10 raised to the power 10 Hz used for radar, infrared region around 10 raised to the power 13 Hz used for heating, ultraviolet region around 10 raised to the power 16 Hz, a component of sun's radiation. The small portion around 10 raised to the power 15 Hz is what is ordinarily called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiation. Different kinds of units are used to represent electromagnetic radiation. These radiations are characterized by the properties namely frequency and wavelength. The SI unit of frequency is Hertz. After Hendrik Hertz, it is defined as the number of waves that pass a given point in 1 second. Wavelength should have the units of length, and as you know, the SI unit of length is meter. Since electromagnetic radiation consists of different kinds of waves of much smaller wavelength, smaller units are used. Figure 2.7 shows various types of electromagnetic radiations which differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiations, regardless of wavelength, travel at the same speed, i.e. 3 into 10 raised to the power 8 meter per second. This is called speed of light and is given the symbol c. The frequency, wavelength and velocity of light c are related by the equation c equals to frequency into wavelength. The other commonly used quantity, especially in spectroscopy, is the wave number. It is defined as the number of wavelengths per unit length. Its units are reciprocal of wavelength unit, i.e. per meter. However, commonly used unit is per centimeter, which is not a SI unit. Particle nature of electromagnetic radiation, Planck's quantum theory. Some of the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even the electromagnetic theory of 19th century known as classical physics. 1. The nature of emission of radiations from hot bodies, black body radiation, ejection of electrons from metal surface when radiation strikes it, photoelectric effect, variation of heat capacity of solids as function of temperature, line spectra of atoms with special reference to hydrogen. It is noteworthy that the first concrete explanation for the phenomena of black body radiation was given by Max Planck in 1900. This phenomena is given below. When solids are heated, they emit radiation over a wide range of wavelengths. For example, when an iron rod is heated in furnace, it first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. In terms of frequency, it means that the frequency of emitted radiation goes from a lower frequency to a higher frequency as the temperature increases. The red color lies in the lower frequency region, while blue color belongs to the higher frequency region of the electromagnetic spectrum. The ideal body, which emits and absorbs radiations of all frequencies, is called a black body, and the radiation emitted by such a body is called black body radiation. The exact frequency distribution of the emitted radiation, i.e. intensity versus frequency curve of the radiation from a black body, depends only on its temperature. At a given temperature, intensity of radiation emitted increases with decrease of wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further decrease of wavelength as shown in figure 2.8. The above experimental result cannot be explained satisfactorily on the basis of wave theory of light. Planck suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner, a belief popular at the time. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of a quantum radiation is proportional to its frequency and is expressed by equation E equals to h nu. The proportionality constant h is known as Planck's constant and has the value of 6.626 into 10 raised to the power minus 34 joules second. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. Photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example potassium, rubidium, cesium, etc., were exposed to a beam of light. The phenomena is called photoelectric effect. The results observed in this experiment were: 1. The electrons are ejected from the metal surface as soon as the beam of light strikes the surface, i.e. there is no time lag between the striking of light beam and the ejection of electrons from its metal surface. 2. The number of electrons ejected is proportional to the intensity or brightness of light. 3. For each metal, there is a characteristic minimum frequency, also known as threshold frequency, below which photoelectric effect is not observed. At frequency which is greater than threshold frequency, the ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of light used. All the above results could not be explained on the basis of laws of classical physics. According to latter, the energy content of the beam of light depends upon the brightness of the light. In other words, number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. It has been observed that though the number of electrons ejected does depend upon the brightness of the light, the kinetic energy of the ejected electrons does not. For example, red light of any brightness may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. But as soon as even a very weak yellow light shines on the potassium metal, the photoelectric effect is observed. The threshold frequency for potassium metal is 5 into 10 raised to the power 14 Hz. Einstein was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. Shining a beam of light onto a metal surface can therefore be viewed as shooting a beam of particles, the photons. When a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Greater the energy possessed by the photon, greater will be the transfer of energy to the electron, and greater the kinetic energy of the ejected electron. In other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. Since the striking photon has energy equals to h nu, and the minimum energy required to eject the electron is h nu naught, also called work function, then the difference in energy h nu minus h nu naught is transferred as the kinetic energy of the photoelectron. Following the conservation of energy principle, the kinetic energy of the ejected electron is given by equation 2.7, which equals h nu equals h nu naught plus half mev square, where me is the mass of electron and v is the velocity with the ejected electron. Lastly, a more intense beam of light consists of larger number of photons. Consequently, the number of electrons ejected is also larger as compared to that in an experiment in which a beam of weaker intensity of light is employed. Dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the one hand, it could explain the black body radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. The only way to resolve this dilemma was to accept the idea that light possesses both particle and wave-like properties, i.e., light has dual behavior. Depending on the experiment, we find that light behaves either as a wave or as a stream of particles. Whenever radiation interacts with matter, it displays particle-like properties in contrast to the wave-like properties, interference and diffraction, which it exhibits when it propagates. This concept was totally alien to the way the scientists thought about matter and radiation, and it took them a long time to become convinced of its validity. It turns out, as you shall see later, that some microscopic particles like electrons also exhibit this wave-particle duality. Evidence for the quantized electronic energy level atomic spectra. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave with shorter wavelength bends more than one with longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out in a series of colored bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shortest wavelength, is deviated the most. The spectrum of white light that we can see ranges from violet at 7.50 into 10 raised to power 14 Hz to red at 4 into 10 raised to power 14 Hz. Such a spectrum is called continuous spectrum. Continuous because violet merges into blue, blue into green, and so on. A similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation. When electromagnetic radiation interacts with matter, atoms, and molecules, may absorb energy and reach to a higher energy state. With higher energy, these are in an unstable state. For returning to the normal, more stable, lower energy states, the atoms and molecules emit radiations in various regions of the electromagnetic spectrum. Emissions and absorption spectra. The spectrum of radiation emitted by substance that has absorbed energy is called an emission spectrum. Atoms, molecules, or ions that have absorbed radiation are said to be excited. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength or frequency of the radiation emitted as the sample gives up the absorbed energy is recorded. An absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelengths. The missing wavelength, which corresponds to the radiation absorbed by the matter, leaves dark spaces in the bright continuous spectrum. The study of emission or absorption spectra is referred to as spectroscopy. The spectrum of the visible light, as discussed above, was continuous, as all wavelengths of the visible light are represented in the spectra. The emission of spectra of atoms in the gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather, they emit light only at specific wavelengths with dark spaces between them. Such spectra are called line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. Line emission spectra are of great interest in the study of electronic structure. Each element has a unique line emission spectrum. The characteristic lines in atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. The exact matching of lines of the emission spectrum of the atoms of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen was one of the first investigators to use line spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by spectroscopic methods. The element helium was discovered in the sun by spectroscopic method. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and the energetically excited hydrogen atom produced emit electromagnetic radiation of discrete frequency. The hydrogen spectrum consists of several series of lines named after the discoverers. Balmer showed in 1885 on the basis of experimental observations that if spectral lines are expressed in terms of wave number, then the visible lines of hydrogen spectrum obey the following formula. Wave number equals 109.677 1 upon 2 square minus 1 upon n square per centimeter, where n is an integer equal to or greater than 3. The series of lines described by this formula are called the Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expressions. Wave number equals 109.677 1 upon n1 square minus 1 upon n2 square per centimeter, where n1 can be 1, 2 and so on, and n2 is n1 plus 1, n1 plus 2 and so on. The value 109.677 centimeter per is called Rydberg constant for hydrogen. The first 5 series of lines that correspond to n1 equals 1, 2, 3, 4, 5 are known as Lyman, Balmer, Paschen, Brackett and P1 series respectively. Table 2.3 shows the series of transitions in the hydrogen spectrum. Figure 2.11 shows the Lyman, Balmer, Paschen series of transitions for. Of all elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes more and more complex for heavier atom. There are, however, certain features which are common to all line spectra, i.e. 1. Line spectrum of element is unique, and 2. There is regularity in the line spectrum of each element. The questions which arise are: what are the reasons for these similarities? Is it something to do with the electronic structure of atoms? These are the questions need to be answered. We shall find later that the answers to these questions provide the key in understanding electronic structure of these elements. Bohr's model for hydrogen atom. Niels Bohr was the first to explain quantitatively the general features of hydrogen atom structure and its spectrum. Though the theory is not the modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectra. Bohr's model for hydrogen atom is based on the following postulates. 1. The electron in hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits, stationary states or allowed energy states. These orbits are arranged concentrically around the nucleus. Second, the energy of an electron in the orbit does not change with time. However, the electron will move from a lower stationary state to a higher stationary state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. The energy change does not take place in a continuous manner. 3. The frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy by delta E is given by frequency equals delta E upon H equals E2 minus E1 upon h, where E1 and E2 are the energies of the lower and higher allowed energy states respectively. This expression is commonly known as Bohr's frequency rule. Fourth, the angular momentum of an electron in a given stationary state can be expressed as MEVR equals n h by 2 pi, where n is integer. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi, that is, why only certain fixed of orbits are allowed. The details regarding the derivation of energies of the stationary states used by Bohr are quite complicated and will be discussed in higher classes. However, according to Bohr's theory of hydrogen atom, the stationary states of electrons are numbered 1, 2, 3. These integral numbers are known as principal quantum numbers. The radii of the stationary states are expressed as Rn equals n square A naught, where A naught is 52.9 picometer. Thus, the radius of the first stationary state, called Bohr's orbit, is 52.9 picometer. Normally, the electron in the hydrogen atom is found in the orbit that is n equals 1. As n increases, the value of R will increase. In other words, the electron will be present away from the nucleus. The most important property associated with the electron is the energy of the stationary state. It is given by expression En equals minus RH 1 upon n square, where RH is called Rydberg constant and its value is 2.18 into 10 raised to the power minus 18 joule. The energy of lowest state, also called as ground state, is E1 equals minus 2.18 into 10 raised to the power minus 18, 1 upon 1 square, which equals minus 2.18 into 10 raised to the power minus 18 joule. The energy of the stationary state for n equals 2 will be minus 0.545 into 10 raised to the power minus 18 joule. Figure 2.11 depicts the energy of different stationary states or energy levels of hydrogen atom. This representation is called an energy level diagram. When the electron is free from the influence of nucleus, the energy is taken as 0. The electron in this situation is associated with the stationary state of principal quantum number equals n equals infinity and is called as ionized hydrogen atom. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted and its energy is lowered. That is the reason for the presence of negative sign in equation 2.13 and depicts the stability relative to the reference state of zero energy and n equals infinity. Bohr's theory can also be applied to the ions containing only one electron, similar to that present in hydrogen atom. For example, He plus, Li2 plus, Be3 plus, and so on. The energies of the stationary states associated with these kinds of ion, also known as hydrogen-like species, are given by the expression En equals minus 2.18 into 10 raised to the power 18 Z square upon n square joules, and the radii by the expression Rn equals 52.9 n square upon Z picometer, where Z is the atomic number and has values 2, 3 for the helium and lithium atoms respectively. From the above equations, it is evident that the value of energy becomes more negative and that of radius becomes smaller with increase of Z. This means that electron will be tightly bound to the nucleus. It is also possible to calculate the velocities of electrons moving in these orbits, although the precise equation is not given here. Qualitatively, the magnitude of velocity of electrons increase with increase of positive charge in the nucleus and decrease with increase of principal quantum number. Explanation of line spectrum of hydrogen. Line spectrum observed in case of hydrogen atom, as mentioned in section 2.3.3, can be explained quantitatively using Bohr's model. According to assumption 2, radiation energy is observed if electron moves from the orbit of smaller principal quantum number to the orbit of higher principal quantum number, whereas the radiation energy is emitted if the electron moves from higher orbit to lower orbit. The energy gap between two orbits is given by equation 2.16. Delta E equals to EF minus EI. Combining, we get delta E upon minus RH upon nf square minus rh upon ni square stand for initial orbits, we get the final equation as 2.18 into 10 raised to the power minus 18 joules, 1 upon n square I minus 1 upon n square f. The frequency associated with the absorption and emission of photon can be evaluated by using equations frequency equals delta E upon h equals RH upon h, 1 minus ni square minus 1 upon nf square, which equals 3.29 into 10 raised to the power 15, 1 upon ni square minus 1 upon nf square hertz. And in terms of wave numbers, it equals to 1.09677 into 10 raised to the power 7 upon bracket 1 upon ni square minus 1 upon nf square per meter. In case of absorption spectrum, NF is greater than Ni and the term in the parenthesis is positive and energy is absorbed. On the other hand, in case of emission spectrum, Ni is greater than NF, delta E is negative and energy is released. The expression is similar to the used by Rydberg, derived empirically using the experimental data available at that time. Further, each spectral line, whether in absorption or emission spectrum, can be associated with particular transition in hydrogen atom. In case of large number of hydrogen atoms, different possible transitions can be observed and thus leading to large number of spectral lines. The brightness or intensity of spectral lines depend upon the number of photons of same wavelength of frequency absorbed or emitted. Limitations of Bohr's model. Bohr's model of hydrogen atom was no doubt an improvement over Rutherford's nuclear model, as it could account for the stability and line spectra of hydrogen atom and hydrogen-like ions. However, Bohr's model was too simple to account for the following points. 1. It fails to account for the finer details, doublet, that is two closely spaced lines, of the hydrogen atom spectrum, observed by using sophisticated spectroscopic techniques. This model is also unable to explain the spectrum of atoms other than hydrogen. For example, helium atom, which possesses only 2 electrons. Further, Bohr's theory was also unable to explain the spreading of spectral lines in the presence of magnetic field, which is called Zeeman effect, or splitting of spectral lines in electric field, which is known as Stark effect. 2. It could not explain the ability of atoms to form molecules by chemical bonds. In other words, taking into account of points mentioned above, one needs a better theory which can explain the salient features of the structure of complex atoms towards quantum mechanical model of the atom. In view of the shortcoming of the Bohr's model, attempts were made to develop a more suitable and general model for atoms. 2 important developments which contributed significantly to the formulation of such model were dual behavior of matter and Heisenberg uncertainty principle. Dual behavior of matter. The French physicist de Broglie in 1924 proposed that matter, like radiation, should also exhibit dual behavior, i.e. both particle and wave-like properties. This means that just as the photon has momentum as well as wavelength, electrons should also have momentum as well as wavelength. De Broglie from this analogy gave the following relation between wavelength and momentum of a material particle. Lambda equals to h by mv equals h by p, where m is the mass of particle, v is velocity, and p its momentum. De Broglie's prediction was confirmed experimentally when it was found that an electron beam undergoes diffraction, a phenomenon characteristic of waves. This fact has been put to use in making an electron microscope, which is based on the wave-like behavior of electrons, just as an ordinary microscope utilizes the wave nature of light. An electron microscope is a powerful tool in modern scientific research because it achieves magnification of about 15 million times. It needs to be noted that according to de Broglie, every object in motion has a wave character. The wavelengths associated with ordinary objects are so short because of their large masses that their wave properties cannot be detected. The wavelengths associated with electrons and other subatomic particles can, however, be detected experimentally. Results obtained from these following problems prove the points quantitatively. Heisenberg's uncertainty principle. Werner Heisenberg, a German physicist, in 1927 stated, "Uncertainty principle, which is the consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously the exact position and exact momentum or velocity of an electron. Mathematically, it can be given by delta x equals delta px, which is greater than h by 4 pi, or delta x into delta v x greater than or equal to h by 4 pi m, where delta x is the uncertainty in position and delta px or delta vx is the uncertainty in momentum or velocity of the particle. If the position of the electron is known with the high degree of accuracy, then the velocity of the electron will be also uncertain. On the other hand, if the velocity of the electron is known precisely, then the position of the electron will be uncertain. Thus, if we carry out some physical measurements on the electron's position or velocity, the outcome will always depict a fuzzy or blurred picture. The uncertainty principle can be best understood with the help of an example. Suppose you are asked to measure the thickness of a sheet of paper with an unmarked meter stick. Obviously, the results obtained would be extremely inaccurate and meaningless. In order to obtain any accuracy, you should use an instrument graduated in units smaller than the thickness of a sheet of paper. Analogously, in order to determine the position of an electron, we must use a meter stick calibrated in units of smaller than the dimensions of an electron. To observe an electron, we can illuminate it with light or electromagnetic radiation. The light used must have a wavelength smaller than the dimensions of an electron. The high momentum photons of such light would change the energy of electrons by collisions. In this process, we no doubt would be able to calculate the positions of the electron, but we would know very little about the velocity of the electron after the collision. Significance of uncertainty principle. One of the important implications of the Heisenberg uncertainty principle is that it rules out existence of definite paths or trajectories of electrons and other similar particles. The trajectory of an object is determined by its location and velocity at various moments. If we know where a body is at a particular instant, and if we know its velocity and the forces acting on it at the instant, we can tell where the body would be sometime later. We therefore conclude that the position of an object and its velocity fix its trajectory. Since for a subatomic object such as an electron, it is not possible simultaneously to determine the position and velocity at any given instant to an arbitrary degree of precision, it is not possible to talk of the trajectory of an electron. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. This can be seen from the following examples. If uncertainty principle is applied to an object of a mass, say about a milligram, then delta V into delta x equals approx 10 raised to power minus 28 meters squared per second. The value of delta V delta x obtained is extremely small and insignificant. Therefore, one may say that in dealing with milligram-sized or heavier objects, the associated uncertainties are hardly of any real consequence. In the case of a microscopic object like an electron, on the other hand, delta V dot delta x obtained is much larger, and such uncertainties are a real consequence. For example, for an electron whose mass is 9 raised to power into 10 raised to power minus 31 kg, according to Heisenberg's certainty principle, delta V dot delta x equals to 10 minus 4 meters squared per second. It therefore means that if one tries to find the exact location of an electron, say to an uncertainty of only 10 raised to power minus 8 meter, then uncertainty delta V in velocity would be approximately 10 raised to power 4 meter per second, which is so large that the classical picture of electrons moving in Bohr's orbits cannot hold good. It therefore means that the precise statements of the position and momentum of electrons have to be replaced by the statements of probability that the electron has at a given position and momentum. This is what happens in the quantum mechanical model of atom. Reasons for the failure of the Bohr model. One can now understand the reasons for the failure of the Bohr model. In Bohr model, an electron is regarded as a charged particle moving in well-defined circular orbits about the nucleus. The wave character of the electron is not considered in Bohr model. Further, an orbit is a clearly defined path, and this path can completely be defined only if both the position and the velocity of the electron are known exactly at the same time. This is not possible according to Heisenberg uncertainty principle. Bohr model of the hydrogen atom, therefore, not only ignores dual behavior of matter but also contradicts Heisenberg uncertainty principle. In view of these inherent weaknesses in the Bohr model, there was no point in extending Bohr model to other atoms. In fact, an insight into the structure of the atom was needed, which could account for wave-particle duality of matter and be consistent with Heisenberg uncertainty principle. This came with the advent of quantum mechanics. Quantum mechanical model of atom. Classical mechanics, based on Newton's laws of motion, successfully describes the motion of all macroscopic objects such as falling stone, orbiting planets, etc., which have essentially a particle-like behavior as shown in the previous section. However, it fails when applied to microscopic objects like electrons, atoms, molecules, etc. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter, especially for subatomic particles and the uncertainty principle. The branch of science that takes into account this dual behavior of matter is called quantum mechanics. Quantum mechanics is a theoretical science that deals with the study of motion of the microscopic objects that have both observable wave-like and particle-like properties. It specifies the laws of motion that these objects obey. When quantum mechanics is applied to microscopic objects, the results are the same as those from the classical mechanics. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrodinger. Here, however, we shall be discussing the quantum mechanics, which is based on the ideas of wave motion. The fundamental equation of quantum mechanics was developed by Schrodinger, and it won him the Nobel Prize in Physics in 1933. This equation, which incorporates wave-particle duality of matter as proposed by de Broglie, is quite complex, and knowledge of higher mathematics is needed to solve it. You will learn its solutions for different systems in higher classes. For a system such as an atom or a molecule whose energy does not change with time, the Schrodinger equation is written as H sigma equals E sigma, where H is a mathematical operator called Hamiltonian. Schrodinger gave a recipe of constructing this operator from the expression for the total energy of the system. The total energy of the system takes into account the total kinetic energies of all the subatomic particles, electrons, nuclei, attractive potential between the electrons and nuclei, and repulsive potential among the electrons and nuclei individually. Solution of this equation gives E and sigma, hydrogen atoms, and the Schrodinger equation. When Schrodinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions of the electron associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers, principal quantum number n, azimuthal quantum number L, and magnetic quantum number m, L, arise as a natural consequence in the solution of the Schrodinger equation. When an electron is in any energy state, the wave function corresponds to the energy state, contains all information about the electron. The wave function is a mathematical function whose value depends upon the coordinates of the electrons in the atom and does not carry any physical meaning. Such wave functions of the hydrogen or hydrogen-like species with one electron are called atomic orbitals. Such wave functions pertaining to one electron species are called one-electron systems. The probability of finding an electron at a point within an atom is proportional to square at that point. The quantum mechanical results of the hydrogen atom successfully predict all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by the Bohr model. Application of Schrodinger equation to multi-electron atoms presents a difficulty. The Schrodinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate methods. Such calculations with the aid of modern computers show orbitals in atoms other than hydrogen do not differ in any radical way from the hydrogen orbital discussed above. The principal difference lies in the consequence of the increased nuclear charge. Because of this all, the orbitals are somewhat contracted. Further, as we shall see later, unlike orbitals of hydrogen or hydrogen-like species whose energy depends only on the quantum number n, the energies of the orbitals in multi-electron atoms depend on quantum number n and L. Orbitals and quantum numbers. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and orientation. An orbital of smaller size means there is no more chance of finding the electron near the nucleus. Similarly, shape and orientation mean there is more probability of finding the electron along certain directions than along others. Atomic orbitals are precisely distinguished by what are known as quantum numbers. Each orbital is designated by 3 quantum numbers labeled as n, L, and ml. The principal quantum number n is positive integer with the value of n equals 1, 2, 3. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen-like species, energy and size of the orbital depends only on n. The principal quantum number also identifies the shell. With the increase in the value of n, the number of allowed orbital increases and are given by n square. All the orbitals of a given value of n constitute a single shell of atom and are represented by the following letters. Size of an orbital increases with the increase of principal quantum number n. In other words, the electron will be located away from the nucleus. Since energy is required in shifting away the negatively charged electrons from the positively charged nucleus, the energy of the orbital will increase with increase of n. Azimuthal quantum number L is also known as orbital angular momentum or subsidiary quantum number. It defines the three-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. That is, for a given value of n, the possible values of L are 0, 1, 2, so forth, and n minus 1. For example, when n equals to 1, value of L is only 0. For n equals to 2, the possible values can be 0 and 1. For n3, the possible values of L are 0 and 1 and 2. Each shell consists of one or more subshells or sublevels. The number of subshells in a principal shell is equal to the value of n. For example, in the first shell, there is only one subshell which corresponds to L equals to 0. There are 2 subshells in the second shell, there are 3 in the third shell, and so on. Each subshell is assigned azimuthal quantum number. Subshells corresponding to different values of L are represented by the following symbols. Table 2.4 shows the permissible values of L for a given principal quantum number and the corresponding subshell notation. Magnetic orbital quantum numbers ml give information about the spatial orientation of the orbital with respect to standard set of coordinate axes. For any subshell, 2L plus 1 values or ml are possible, and these values are given by ml equals minus L minus L minus 1 minus L minus 2 0 1 L minus 2 L minus 1 L. Thus, for L equals to 0, the only permitted value of ml0 is 1s orbital. For L1, m1 can be minus 1 0 and plus 1 can be equal to 3p orbitals. For L equals to 2, ml equals to minus 2 minus 1 0 plus 1 and plus 2, 5d orbitals. It should be noted that the values of ml are derived from L and the value of L are derived from n. Each orbital in an atom therefore is defined by a set of values for nl and ml. An orbital described by the quantum numbers is an orbital in the p subshell of the second shell. The following chart gives the relation between the subshells and the given number of orbitals associated with it. Electron spin s. The 3 quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape, and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms. That is, some of the lines actually occur in doublets, triplets. This suggests the presence of a few more energy levels than predicted by 3 quantum numbers. In 1925, George Heisenberg and Samuel Goudsmit proposed the presence of the 4th quantum number known as electron spin quantum number ms. An electron spins around its own axis much in a similar way as Earth spins around its own axis while revolving around the Sun. In other words, an electron has, besides charge and mass, intrinsic spin angular quantum number. Spin angular momentum of the electron, a vector quantity, can have two orientations relative to the chosen axis. These two orientations are distinguished by the spin quantum numbers ms, which can take the value of plus half or minus half. These are called the two spin states of the electron and are normally represented by two arrows, spin up and spin down. Two electrons that have different ms values are said to have opposite spin. An orbital can not hold more than two electrons, and these two electrons should have opposite spins. To sum up, the four quantum numbers provide the following information. N defines the shell, determines the size of the orbital, and also to a large extent the energy of the orbital. There are n subshells in the nth shell. L identifies the subshell and determines the shape of the orbital. There are 2 L plus 1 orbitals of each type in subshell, that is, 1 s orbital, 3 p orbitals, and 5 d orbitals per subshell. To some extent, L also determines the energy of the orbital in multi-electron atom. ML designates the orientation of the orbital. For a given value of L, ML has 2L plus 1 values, the same as the number of orbitals per subshell. It means that the number of orbitals is equal to the number of ways in which they are oriented. MS refers to the orientation of the spin of the electron. Shapes of atomic orbitals. The orbital wave function for an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave functions as a function of r are different, which gives plots for 1s and 2s orbital. According to the German physicist Max Born, the square of the wave function at a point give the probability of density of the electron at the point. The variation as a function of r for 1s and 2s orbitals is given in figure 2.12b. Here again, you may note that the curves for 1s and 2s orbitals are different. It may be noted that for 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as you move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to the 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces or simply nodes. In general, it has been found that ns orbital has n-1 nodes, that is, number of nodes increases with increase of principal quantum numbers n. In other words, the number of nodes of 2s is 1, 2 for 3s, and so on. These probability density variations can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in a region represent electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals can give a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in space for an orbital on which the value of probability density is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of a constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say 90%. The boundary surface diagram for 1s and 2s orbitals are given in figure 2.13b. One may ask a question: why do we not draw a boundary surface diagram which bounds the region in which the probability of finding the electron is 100%? The answer to this question is that the probability density has always some value, howsoever small it may be at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for s orbital is actually a sphere centered on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the s orbitals are spherical symmetric. That is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of the s orbital increases with increase in n, that is 4s greater than 3s greater than 2s greater than 1s, and the electron is located further away from the nucleus as the principal quantum number increases. Boundary surface diagrams for 3p orbitals L equals to 1 are shown in figure 2.14. In these diagrams, the nucleus is at the origin. Here, unlike s orbitals, the boundary surface diagrams are not spherical. Instead, each p orbital consists of two sections called lobes that are on either side of the plane that passes through the nucleus. The probability density of function is 0 on the plane where the two lobes touch each other. The size, shape, and energy of the three orbitals are identical. They differ, however, in the way the lobes are oriented. Since the lobes may be considered to lie along x, y, z axis, they are given the designations 2px, 2py, and 2pz. It should be understood, however, that there is no simple relation between the values of ml, -1, 0, and +1, and the x, y, z directions. For our purpose, it is sufficient to remember that because there are three possible values of ml, there are therefore three p orbitals whose axes are mutually perpendicular. Like s orbitals, p orbitals increase in size and energy with increase in the principal quantum number, and hence the order of the energy and size of various p orbitals is 4p greater than 3p greater than 2p. Further, like s orbitals, the probability density functions of p orbital also pass through value 0. Besides, at 0 and infinite distance, as the distance from the nucleus increases, the number of nodes are given by n-2. That is, number of radial nodes is 1 for 3p orbital, 2 for 4p orbital, and so on. For L equals to 2, the orbital is known as d orbital, and the minimum value of principal quantum number n has to be 3. As for the value of L cannot be greater than n-1, there are 5 ml values, -2, -1, 0, +1, and +2 for L2, and thus there are 5 d orbitals. The boundary surface diagram of d orbital is shown in figure 2.15. The 5 d orbitals are designated as dxy, dyz, dxz, dx square minus y square, and dz square. The shapes of the first 4d orbitals are similar to each other, whereas that of the fifth one, dz square, is different from others, but all 5 3d orbitals are equivalent in energy. The d orbitals for which n is greater than 3 also have shapes similar to 3d orbital but differ in energy and size. Besides the radial nodes, probability density function is 0. The probability density functions for the np and nd orbitals are 0 at the plane passing through the nucleus. For example, in case of pz orbital, xy plane is a nodal plane. In case of dxy orbital, there are two nodal planes passing through the origin and bisecting the xy plane containing z axis. These are called angular nodes, and number of angular nodes are given by L, i.e. one angular node for p orbitals, two angular nodes for d orbitals, and so on. The total number of nodes are given by n-1, i.e. sum of L angular nodes and n-L-1 radial nodes. Energies of orbitals. The energy of an electron in a hydrogen atom is determined solely by the principal quantum number. Thus, the energy of the orbitals increases as follows, and is depicted in figure 2.16. Although the shapes of 2s and 2p orbitals are different, an electron has the same energy when it is in the 2s orbital as when it is present in 2p orbital. The orbitals having the same energy are called degenerate. The 1s orbital in a hydrogen atom, as said earlier, corresponds to the most stable condition and is called ground state, and an electron residing in this orbital is more strongly held by the nucleus. An electron in the 2s, 2p or higher orbitals in a hydrogen atom is in excited state. The energy of an electron in a multi-electron atom, unlike that of the hydrogen atom, depends not only on its principal quantum number but also on its azimuthal quantum number, that is, for a given principal quantum number S, PDF, all have different energies. The main reason for having different energies of the subshells is the mutual repulsion among the electrons in a multi-electron atoms. The only electrical interaction present in hydrogen atom is the attraction between negatively charged electron and the positively charged nucleus. In multi-electron atoms, besides the presence of attraction between the electron and nucleus, there are repulsion terms between every electron and other electrons present in the atom. Thus, the stability of an electron in multi-electron atom is because of total attraction. Attractive interactions are more than the repulsive interactions. In general, the repulsive interactions of the electrons in the outer shell with the electrons in the inner shell are more important. On the other hand, the attractive interactions of an electron increases with increase of positive charge on the nucleus. Due to the presence of electrons in the inner shells, the electrons in the outer shell will not experience the full positive charge of the nucleus Ze. The effect will be lower due to the partial screening of positive charge on the nucleus by the inner shell electrons. This is known as the shielding of the outer shell electrons from the nucleus by the inner shell electrons, and the net positive charge experienced by the outer electrons is known as the effective nuclear charge Z effective E. Despite the shielding of the outer electrons from the nucleus by the inner shell electrons, the attractive force experienced by outer shell electrons increases with increase of nuclear charge. In other words, the energy of interaction between the nucleus and the electron decreases with the increase of atomic number Z. Both the attractive and repulsive interactions depend upon the shell and shape of the orbital in which the electron is present. For example, electrons present in spherical shaped s orbital shields the outer electron from the nucleus more effectively as compared to electrons present in p orbital. Similarly, electrons present in p orbitals shield the outer electrons from the nucleus more than the electrons present in d orbitals, even though all these orbitals are present in the same shell. Further, within a shell, due to spherical shape of s orbital, the s orbital electron spends more time close to the nucleus in comparison to p orbital electron, which spends more time in the vicinity of nucleus in comparison to d orbital electron. In other words, for a given shell, the Z effective experienced by the electron decreases with increase in azimuthal quantum number. That is, the s orbital electron will be more tightly bound to the nucleus than p orbital electron, which in turn will be better tightly bound than the d orbital electron. The energy of electrons in s orbital will be lower, i.e. more negative than that of p orbital electron, which will have less energy than that of d orbital electron, and so on. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to splitting of energy levels within the same shell. That is, energy of electron in an orbital, as mentioned earlier, depends upon the values of n and l. Mathematically, the dependence of energies of orbitals on n and l are quite complicated, but one simple rule is that the lower the value of n plus L for an orbital, the lower is its energy. If two orbitals have the same value of n plus L, the orbital with lower value of n will have the lower energy. The table 2.5 illustrates that n plus L rule depicts the energy levels of multi-electron atoms. It may be noted that different subshells of a particular shell have different energy in case of multi-electron atoms. However, in a hydrogen atom, they have the same energy. Lastly, it may be mentioned here that energies of the orbitals in the same subshell decrease with increase in atomic number Z effective. For example, energy of 2s orbital of hydrogen atom is greater than the 2s orbital of lithium, and that of lithium is greater than that of sodium, and so on. Filling of orbitals in atoms. The filling of electrons into the orbitals of different atoms takes place according to Bohr principle, which is based on Paulie's exclusion principle, the Hunt rule of maximum multiplicity, and the relative energies of the orbital. Bohr principle. The word Bohr in German means building up. The building up of orbitals mean that filling up of orbitals with electrons. The principle states in the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, electrons first occupy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. The order in which the energies of the orbital increase, and hence the order in which the orbitals are filled, are as follows. The order may be remembered by using the method given in figure 2.17. Starting from the top, the direction of the arrows give the order of filling of orbitals, that is starting from right top to bottom left. Paulie's exclusion principle. The number of electrons to be filled in various orbitals is restricted by the exclusion principle given by the Austrian scientist Wolfgang Paulie. According to this principle, no two electrons in an atom can have the same set of 4 quantum numbers. Pauli exclusion principle can also be stated as only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. This means that the 2 electrons can have the same value of 3 quantum numbers n, l, ml, but must have the opposite spin quantum number. The restriction imposed by Paulie's exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any subshell. For example, subshell 1s comprises of one orbital, and thus the maximum number of electrons present in 1s subshell can be 2 in PD subshells. The maximum number of electrons can be 6 and 10 and so on. This can be summed up as the maximum number of electrons in the shell with principal quantum number n is equal to 2n square. Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into the orbitals belonging to the same subshell, called degenerate orbitals. It states pairing of electrons in the orbitals belonging to the same subshell PD or F does not take place until each orbital belonging to that subshell has got one electron each, i.e. it is singly occupied. Since there are 3p, 5d and 7f orbitals, therefore the pairing of electrons will start in the p, d and f orbitals with the entry of 4th, 6th and 8th electron respectively. It has been observed that half-filled and fully filled degenerate set of orbitals acquire extra stability due to their symmetry. Electronic configuration of atoms. The distribution of electrons into orbitals of an atom is called its electronic configuration. If one keeps in mind the basic rules which govern the filling of different atomic orbitals, the electronic configurations of different atoms can be written very easily. The electronic configuration of different atoms can be represented in two ways: S, A, P, B, D, C notation or orbital diagrams. In the first notation, the subshell is represented by the respective letter symbol, and the number of electrons present in the subshell is depicted as the superscript. The similar subshell represented for different shells is differentiated by writing the principal quantum number before the respective subshell. In the second notation, each orbital of the subshell is represented by a box, and the electron is represented by an arrow, a positive spin, or a down arrow, a negative spin. The advantage of second notation over the first is that it represents all the 4 quantum numbers. The hydrogen atom has only one electron which goes in the orbital with the lowest energy, namely 1s. The electronic configuration of the hydrogen atom is 1s1, meaning that it only has one electron in the 1s orbital. The second electron in helium can also occupy the 1s orbital. Its configuration is therefore 1s2. As mentioned above, the 2 electrons differ from each other with opposite spin, as can be seen from the orbital diagram below. The third electron of lithium is not allowed in the first 1s orbital because of Paulie's exclusion principle. It therefore takes the next available choice, namely the 2s orbital. The electronic configuration of Li of lithium is 1s square 2s1. The 2s orbital can accommodate one more electron. The configuration of beryllium atom is therefore 1s square 2s square. In the next 6 elements, boron, carbon, nitrogen, oxygen and neon, 2p orbital gets progressively filled. This process is completed with the neon atom. The orbital picture of these elements can be represented as follows. The electronic configuration of the elements sodium to argon follow exactly the same pattern as the elements from lithium to neon, with the difference that the 3s and 3p orbitals are getting filled now. This process can be simplified if we represent the total number of electrons in the first 2 shells by the name of element neon. The electronic configuration of the elements from sodium to argon can be written as Na Ne3s1 or argon Ne3s square 3p6. The electrons in the completely filled shells are known as core electrons, and the electrons that are added to the electronic shell with the highest principal quantum numbers are called valence electrons. For example, the electrons in neon are the core electrons, and the electrons from sodium to argon are the valence electrons. In potassium and calcium, the 4s orbital, being lower in energy than 3d orbitals, is occupied by 1 and 2 electrons respectively. In potassium and calcium, the 4s orbitals, being lower in energy than the 3d orbitals, is occupied by 1 and 2 electrons respectively. A new pattern is followed, beginning with scandium. The 3d orbitals, being lower in energy than the 4p orbitals, is filled first. Consequently, in the next 10 elements, scandium, titanium, vanadium, chromium, magnesium, iron, cobalt, nickel, copper, and zinc, the 5 3d orbitals are progressively occupied. We may be puzzled by the fact that chromium and copper have 5 and 10 electrons in 3d orbitals, rather than 4 and 9, as their positions would have indicated, with 2 electrons in the 4s orbital. The reason is that fully filled orbitals and half-filled orbitals have extra stability. that is lower energy. Thus, P3P, 6P5, D10, F7, F14, etc. configurations are either half-filled or fully filled are more stable. Chromium and copper, therefore, adopt the D5 and D10 configurations. With the saturation of the 3D orbitals, the filling of the 4p orbital starts at gallium and is completed at krypton. In the next 18 elements, from rubidium to xenon, the pattern of filling 5s, 4d and 3p orbitals are similar to that of 4s, 3d, 4p orbitals discussed above. Then comes the turn of 6s orbitals. In cesium and the barium, this orbital contains 1 and 2 electrons respectively. Then from the lanthanum to mercury, the filling of electrons takes place in 4f, 5d orbitals. After this, filling of 6p, then 7s, and finally 5f and 6d orbitals takes place. The element after uranium are all short-lived and all of them are produced artificially. The electronic configurations of known elements are tabulated in table 2.6. One may ask, what is the utility of knowing the electron configuration? The modern approach to the chemistry in fact depends almost entirely on electronic distribution to understand and explain chemical behavior. For example, questions like why two or more atoms combine to form molecules, why some elements are metals while others are non-metals, why elements like helium and argon are not reactive but elements like halogens are reactive, find simple explanation from the electronic configurations. These questions have no answer in Daltonian model of atom. A detailed understanding of the electronic structure of atom is therefore very essential for getting an insight into the various aspects of modern chemical knowledge. Stability of completely filled and half-filled subshells. The ground state electronic configuration of the atom of an element always corresponds to the state of the lowest total electronic energy. The electronic configurations of most of the atoms follow the basic rules. However, in certain elements such as copper or Ca, where the two subshells 4s and 3d differ slightly in their energies, an electron shifts from a subshell of lower energy to a subshell of higher energy, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. The valence electron configuration of Cr and Cu therefore are 3d 5 4s1, 3d 10 4s1 respectively, and not 3d 4 4s2. It has been found that there is extra stability associated with these electronic configurations.